All of you write your roll number in the chat box. I'm sharing my screen. Screen is visible?
Yes, ma'am.
Okay. Let's wait for 2-3 minutes. Let others come. 17. This part was clear. This was just the review we have discussed earlier. Okay. Well, today basically we'll start with this. What you're seeing in the screen, tension test, and there is a stress strain graph. It is visible? It is visible? Hello?
Yes, ma'am, PC.
Okay. What I have thought today that I'll make a video beforehand. Okay. Suppose if we have to class on Monday, we have two class, right? In the first class, I'll give you the video, or I'll do that on Sunday itself. I'll share the video. You all go through the video, and in the morning, first class go through the video. Then we'll discuss the what you have not understood in the second class. That will be easy, I guess. What do you suggest? What do you guys suggest? Tell me. Because I have very network issues. So I'm thinking of making videos like practical, all the videos, all the class videos. Then I'll share beforehand. You go through the video. Then in the class, we'll just discuss what are the things you have found difficult to understand. In that way, it will be easy for me. What about what you guys suggest? Tell me. Unmute yourself and share what I should do so that you guys understand. Otherwise, yeah.
Ma'am, you will make video of the class
Yes, I'm thinking of
and you will share beforehand.
yes, yes, yes. What do you say? What your point in this? And any suggestion from your side?
It's good. It
That
will
will
save time.
yes. It no, you have to come to the class. It won't save your time. It will take much time.
Yeah, yeah.
It will take my time. It will take your time, but it will be easy for you to understand. Otherwise, if we just focus on the network issue all the way, we won't be able to cover the whole syllabus, right? So I'll do that.
Yeah.
I'll make video beforehand and share with you. You guys go through the video. If possible, we'll go through the video in the first class itself. Then second class, we'll discuss what you haven't understand. Okay, is that fine?
Ma'am.
Okay. Okay, 24 student came. Let's start the class. Hope everyone wrote their roll number. Okay. So this is our typically stress strain graph. So what is the need of stress strain graph? Basically, we to know the behavior. What will be the behavior of the material? We basically need tension. We basically do tension test. What happen in tension test? It will elongate. It will elongate a member. Okay, suppose this is your member in tension test. There is a spring attached here. Spring attached. It will elongate this member. Okay, then that is basically a tension test. You can google this about this test later on. So basically my point is to my focus is today's focus is stress strain diagram. Okay, what is strain diagram? So so basically To examine material properties, we perform tension test. In graphing the results, we will plot stress strain instead of force and change in length. This allows for the removal of geometry from the problem and allows the results to be used in different geometrical shapes of the same material. See, we'll discuss the detail of this graph. First, see, this is the linear part. Why linear? Because whatever you applied stress, it will give same strain till this point. Okay, after this point it starts yielding. It will yield, and at some point it will get fractured. Okay, so this part is your non-linear area, this part is your linear area. Okay, this is the forget about the formula right now. So this is the linear part, this is the non-linear part. This is the yield point. Yield point means from this point your structure will start yielding. It will show deformation, and it will deform, and at some point it will get fractured or deformed. It will get failed. So this is the typical normal stress test diagram. Different material will have different diagram. Okay, I have taken a simple stress strain diagram. You can take you can draw a stress strain diagram of rubber. You can draw a stress strain diagram of aluminium foil, steel. Every material you can draw this stress strain diagram to just to know the behavior. Okay, so let's discuss one. So in the x-axis you have strain, and in the y-axis you have this stress, and we'll start with the zero stress strain. Okay, so I've taken a suppose spring. I'm drawing a stress strain curve of a spring. So at first when you stretch a spring to a certain load, it will show you same behavior. Whatever you give, whenever you give stress or stress in terms of force, whenever you give a force, it will give a strain. When you suppose, just imagine I'm pulling out a very hard spring, it will stretch out. Okay, right? When I apply the force, it will stretch out. But when I leave the force, it will regain its shape, right? So till this point, what it is point called proportionally limit. This point in the curve is represented to this proportional limit, and this region is called linear region. Up to this point, your spring will regain its own shape. Okay, whenever you give stress, it will give a strain. Whenever you remove that stress, it will come back to its original shape. So this is called linear region. Some are in the waiting room. Let me admit them. Okay. Okay. So the slope of this curve is nothing but your E, Young's modulus. You have got this word Young's modulus. So Young's modulus is nothing but it's a slope of this stress strain curve in the linear region. So we're done with this part. Next, come to a point. When you give a stress, now it will start yielding. Okay, it will in this region your body tries to come into its original shape. Okay, till this point at this point it starts yielding, and this point is called yield stress. From this point your spring will not come back to its original shape, or your structure will not come back to its original shape. It will start deforming. So this point corresponding to x-axis is called, this region is called elastic region, and this point is called yield stress. The point from where your structure or member will start yielding, it will get deformed. So see, now the curve goes straight. This means whatever you applied the stress, it will get elongated. This is the sign that it will stretched out. It will be stretched out. This is a very big section. You cannot describe this section. Okay. See, those who have written their attendance, fine, but I'll take the attendance one at the last moment. I'll just see the participant list. So don't come to the class, give attendance, and left the class. Okay. At the end of the class or in the middle of the class, I'll take the screenshot of the participant list. Anyways, leave that part. So this is the very long area. Okay, I have represented this section. By this, that means This is very long. Means you will the fracture point is very far. This is very long area. This region is called perfectly plastic yielding. This means it will, here it was an elastic region, now it comes to a plastic region. Whatever will be the stress, now it will get elongated, elongated and elongated. It will get increased. So this is nothing but perfectly elastic yielding region. Now from this point to this point, at this point, this is ultimate stress. Means after this point, your structure cannot handle any stress. Okay, till here it will get some stress and it will start yielding. It start get elongation. So this we'll discuss this portion in the next classes. Brief, very descriptively. Just I'm telling the brief part. So from plastic yielding point to the yield stress, this region is nothing but strain hardening. We'll discuss what is strain hardening. This is the point where ultimate stress. After this point, your body cannot take any stress. Okay. Now from this point, it will start fractures. Okay, it will get deformed, and from this point to this point is necking. Sometimes this graph comes to, it will show you a portion and I will ask you which portion it is. Very important graph from gate. In future you will appear for gate. Very important graph for your future point of view also. So basically you have understood, I guess. This is the stress strain graph. There are different components. You have elastic region, you have plastic region, then strain hardening and then necking. First your material will behave elastically, then it will comes to plastic, and then it will get fracture. Okay. So Hooke's law, you have got Hooke's law, right? Earlier you might have gone through Hooke's law. So Hooke's law, what? Hooke's law is generally valid for linear elastic region. So our linear elastic region is how much? This is our linear elastic region. So Hooke's law is valid for linear elastic region. It is nothing but stress is directly proportional to strain. This part, I told you na, this part, in this part stress is directly proportional to strain. So stress is nothing but sigma. This part sigma is directly proportional to which is strain E, right? If I remove this directly proportional to, we can represent by a constant of proportionality E, which is nothing but Young's modulus. So this is what? Hooke's law. Stress is directly proportional to strain is defined as Hooke's law, and this directly proportional is replaced by a E value, which is Young's modulus. Correct? So from this diagram we'll study some properties of the material. Suppose stiffness. How the stiff is the body? Okay, now tell me, if the slope of the curve is more, or Young's modulus is more, so that will be more stiff, or Young's modulus less, that will be more stiff. Which one will be more stiff? Anyone? Which one will be more stiff? The one which have more Young's modulus, or the one which have less Young's modulus? Anyone? Anything? See, your stiffness. What is stiffness? Suppose a person is standing in front of me. If I give him a push, if my push has the capability to move him, then it has less stiffness, right? If I give a push that he doesn't move, then it will be stiff. That is the stiffness. Suppose any member is getting a load. Suppose this is a member. I'm applying a load. Suppose I have applied a 50 kilonewton. This is the body. Suppose it was straight body. Huh? Just imagine this is a straight body. I have applied a load 50 kilonewton. Suppose it get deformed in this direction. So this doesn't have stiffness comparison to this. Okay, that is stiffness. So your stiffness, the stiffness of a member is depend on Young's modulus of elasticity. If the curve is this much, your slope will be less. Okay. If the curve goes in this way, your slope will be less. Slope less means Young's modulus less. so it will have less steepness. If the curve is like this, it will have more slope, so it will have more steep. Okay. So we first discuss the property stiffness and Hooke's law. Next, come to the strength part. What is strength? How? What strength defines? Stress defined means capacity of high stress or ultimate stress. This point will define your strength of the member. What is the ultimate stress? How much will be the ultimate stress? Suppose you have been given another curve like this. You have been given another curve of like this, which has yield stress at this point. Suppose this curve has yield stress at this point and this curve has yield stress at this point. So which one have yield stress more? This one? Okay. So the more which one will have ultimate stress, that will be more strength. Then next move to the toughness. Capacity for energy absorption. So area under stress strain curve, what the area between this curve, this area. How much is the area of this curve? Suppose this is one curve. How much area is in this curve? Suppose this area is more or this area is more. So you have to find, that will give you toughness. Next, see, write down these words and see what does mean. Write strength, toughness, what is resilience, ductility, brittleness. Go search these words and understand. Okay, if you don't understand, then we'll discuss in the next class. Then resilience, capacity for deformation elastically, area under elastic region. So this area, this is the elastic region, this area represents your resilience. Then next will ductility, capacity for high deformation. So what is the strain? That will represent your ductility. It can be moved, it cannot be moved, that will give you ductility. Then brittleness, what is the capacity, low capacity of deformation and strain. If the capacity of strain is high, then it will come to ductility. In the capacity of deformation is low, then it will come to brittleness. Hope this part is clear. Till then, this part is clear or not? This curve is clear or not? Please respond. This part of the curve is clear or not?
Yes, ma'am.
Clear?
Yes, ma'am.
Okay.
Yes.
So I thought of giving this worksheet as a, suppose this is the stress strain curve. Okay. This is a curve of common magnesium alloy. This is a curve of common general purpose aluminum alloy. And this is a curve of A36 standard structural steel alloy. Please write down these questions. What is the approximate modulus? First draw this diagram. Or take out the screenshot. I'll share the problem with you. Okay, I'll share this problem with you. Actually, I'll share this PPT itself today. So these are the different curves, stress strain curve of three different aluminum. This one is for magnesium alloy, this one for aluminum alloy, this one for structural steel alloy. Okay, here different stress and strain is given to you. What you have to do, you have to first find approximate modulus of elasticity for A36 steel. Which one is A36 steel? This one. For this curve, you have to find E value. Okay, stress and strain is given to you. You have to find E value for this. In the next question, you have to find ultimate strength of A36 steel. Then after elasticity, you have to find ultimate strength. Now, how can you find the strength? How can you find out the strength? From the stress value. What will be the stress value? You can find out the strength. Then approximate proportional limit of the common magnesium alloy. What will be the proportional limit? What will be the proportional limit for magnesium alloy? For this alloy, what will be the proportional limit? You have to see, you have to make a curve till which point this curve doesn't change its shape. See, it comes straight. At this point, it changes its shape, so you have to draw a line. Try it, okay? Try this problem by yourself. We'll discuss the solution. I have the solution also. We'll discuss the solution in the next class on Wednesday. Okay? This much will be sufficient, I guess, for today. I'll stop sharing my screen. All of you wrote their roll number? Let me take out the roll number. Let me take. I'll do one thing. I'll share the number of absentees also, so that those who were present in the class, sometime it gets missed out. Last class, one student get missed. He was kicked out from the class. I don't know who kicked out. I haven't kicked out him, but he was present in the class. But I didn't see him in the participant list. So I'll mention the list of absent in the class. Please get it done. All the feedback. And I'll do one thing. I'll make a video. Okay, that will be more easy, I guess. To go beforehand all the videos. Then in the class we'll discuss. See, in chat box there are more roll number than in participant list. Many of them came to the class and they left the class. Very smart. Hope the stress strain curve is little bit clear. Okay, I'm ending the class. You can leave now. Thank you.